Today we're going to be talking about RF filter design. Now, these days, the actual design of a filter is pretty straightforward. You've got tons of design tools and simulations that you can run to put together, pretty much a perfect RF filter. The trick is actually realizing that same simulated performance in the real world. Take this filter, for example. This was designed using a filter design tool. It's set up for 50 ohm input and output impedances, and it is a second order Butterworth bandpass filter. And you can see you have two tuned elements here, and they are coupled together with a coupling capacitor, and the input and output is also coupled with coupling capacitors as well. So the actual component selection for this is all done by the design tool, obviously. This is set up to have a 6 megahertz 3 dB bandwidth with a center frequency of 137 megahertz. And on paper and in the simulator, this works wonderfully. But when you go to actually build this in the real world, there are a couple things that can trip you up pretty quickly. The first thing to consider is the queue of your components, because most design tools and simulators assume practically lossless components, which you're certainly not going to get in the real world, especially when it comes to your inductors. The capacitors usually have very high Q, but the inductors can be lossy. So just because your simulation says that you'll have very little or no loss in your passband, don't expect that to happen when you actually build the filter. Typically, you can expect 1 to 3 dB of loss in the passband, depending on primarily the Q of your inductors. The next thing to consider is stray capacitance, component tolerance, and tolerance over temperature and time, because components do wear out and they do drift over time. So if these two capacitors here, which are part of these two tuned circuits, change by 1 picofarad, that can knock this filter's passband completely out of the range of frequencies that I actually want to pass. Now you can easily pick up a picofarad of capacitance just from the stray capacitance on the board. Not to mention, these inductors, if you want high Q inductors, will typically be hand wound, so they're not going to be exactly 100 nanohenries or whatever your nominal value is there. So these are going to change the center frequency of your bandpass filter, and they can change it quite drastically. So what I typically do is I make these capacitors variable. Just some trimmer capacitors so you can really dial in the center frequency of the filter. Now optionally, if you've hand wound these coils, you can kind of pull the coils apart so they're spread apart a little bit more, or push the turns together so they're a little closer, and you can vary the resonance of these tuned circuits that way. But I actually find that to be very temperamental and really a pain to do. So I much prefer to have some good quality trim caps in here to tweak the center of the bandpass filter if necessary. Now, while these two tuned circuits are going to determine the center frequency of your bandpass filter, this coupling capacitor is actually going to control the shape of your bandpass filter. Now, an ideal bandpass filter is nice and flat through the passband, and then it sharply cuts off in the stopband. But that's only going to happen if this coupling capacitor is just right. So it's called critical coupling. If your capacitor is too large here, you're actually going to be overcoupled, and what you'll see is instead of a flat passband, you'll kind of have this double hump in the passband. Likewise, if this is too small, you'll have undercoupling, and you only have one peak in the passband, but it'll be very narrow, and you typically have a lot of loss in your passband as well. It's also very common, as you probably noticed, for this coupling capacitor to be quite small in value. This is only supposed to be 0.4 picofarads. Now you can achieve a small capacitance in a couple of ways. Obviously you could put a bunch of larger capacitors in series. However, I prefer to just take two insulated wires and twist them together, because really all a capacitor is two conductive pieces of metal that come close to each other but don't actually touch. So the tighter you twist them together, the more capacitance you have, and if you kind of untwist them a bit, you get less capacitance. So it's a very cheap and easy way to give yourself a variable, very low value capacitor here, so you can really dial in that coupling capacitor just right. So I have the filter built up on the bench here, and you can see I've used a couple of good quality air variable trim caps here. Those are in parallel with these inductors here, forming the two tuned circuits. And these inductors are just 6 turns of 18 gauge enamel wire on a 3/16 inch diameter. For the input and output coupling capacitors, I just have a couple of 3.3 picofarad NPO types, and of course we have the coupling capacitor in between the two tuning elements formed by these two wires here. So let's hook this up to the spectrum analyzer and see how it performs. So I have the filter hooked up to the spectrum analyzer, and right now I'm showing a span of 100 to 200 megahertz here. And you can see the 3 dB cutoff points are at 134.5 megahertz and 141 megahertz. And at the center frequency here, which is just about 137 megahertz, we have just about 1 dB of loss here. So that's pretty darn good. And this filter matches almost exactly what was predicted in the simulation. Now, of course, it did take a bit of tweaking to get it to this point. Obviously, I have 3 capacitors that I can vary here. If I modify the air variable capacitors, I can change the center frequency up or down as I need to. And if I play around with that coupling capacitor, I can kind of change the shape of the bandwidth there in the middle. So you can see I'm undercoupled here, so I'm getting a bit of a narrower bandwidth, but I'm also getting a lot more loss. So if I kind of twist those wires back together, I start getting a little less loss. I can kind of play around with that till I get it just right. Now, as you can see, there is a sharper cutoff here down towards the lower frequencies than there is towards the higher frequencies. And that's actually expected. When you have a bandpass filter that's coupled with capacitors, typically this is the response you'll get. You'll get more attenuation on lower frequencies than you do on the higher frequencies. And in this particular application, that's actually desirable. These stronger frequencies that I want to reject are actually down below my center frequency. But if you wanted to have steeper attenuation on the higher frequencies instead, you could use inductors to couple the elements together rather than capacitors. So this filter seems to be performing pretty well, at least in the 100 to 200 megahertz range. But if I change my frequency span to the full span of the spectrum analyzer, which is up to 1.5 gigahertz, you can see that up at higher frequencies, we're really not getting a lot of attenuation at all. In fact, as we approach 1 gigahertz here, we're only getting about maybe 5 or 6 dB of attenuation. And the reason for that is that we don't have any shielding between the tuned elements in our filter. So here are the 2 tuned elements in our filter, and there's no shielding in between them here. And that means that at higher frequencies, it's easier to get some unwanted coupling between these and basically get some pass-through at higher frequencies. So you're not attenuating those higher frequencies as much as you might like. And the solution, of course, is to add some shielding. So this is the exact same filter. I'm using some piston trim caps here instead of the air variable caps I had in the other filter. They're just a little easier to tweak the filter with because they're multi-turn. But otherwise, the filter is exactly the same, using the same inductors, same coupling capacitors here. I've got my little 2-wire coupling capacitor here, you can see. But I've added just a bit of shielding here, and this is just built out of some scrap PCB that I cut up. And I've drilled a little hole through the shield here to pass that coupling capacitor through. But just this little bit of shielding here can make all the difference in the world. So with the shielded filter hooked up to the spectrum analyzer, you can see that the response shape is pretty much exactly the same in the 100 to 200 megahertz range. My 3 dB cutoffs are at 133 megahertz and 141 megahertz, so a little bit of a wider bandwidth than the first filter. If you look at the center frequency, we're actually getting quite a good insertion loss here, less than 1 dB. And that's pretty typical of most bandpass filters. All else being equal, if you have a wider passband, you're going to have less insertion loss in there. But this response is certainly more than adequate for what I need this filter to do. The real question is, how does this filter perform at higher frequencies? So if we go to the full span here of the spectrum analyzer, you can see we're getting much improved attenuation up at these higher frequencies. They're all staying right about negative 30 dB here, instead of peaking up to negative 5 or negative 6 dB like we had before. So just that little bit of extra shielding in the filter design really helps to attenuate those higher frequencies. So don't be afraid to build your own filters at home. With a bit of attention to detail, some experimentation and adjustment, you can get some really impressive responses from relatively simple filters that you can build yourself. So I hope you enjoyed this video, and if you did, be sure to give it a thumbs up. And if you have any questions, suggestions, or corrections, be sure to leave them in the comments section below. Thanks for watching.